So we have seen that in sleep and wake up, whenever a process is sleeping and when other process is trying to wake it up, that wake up signal is going to get lost if the process is not actually sleeping, right? So instead of using that, this Dijkstra has proposed that don't directly send the wake up signal to them to the sleeping process. You just write the signal in a variable so that it will be stored and it will be there and anyone can use it whenever they want it, right? So semaphores provide a way using which we can store the wake up calls. So this variable will contain all the wake up calls. So any process before going to sleep, it can just check if some other process has already given a wake up, and if it is true, then it need not go to sleep. That is how this semaphores will work, right? And that is how semaphores will work. That is the main use. But then the problem with semaphores is if they are implemented at the user level, then at the same time someone will try to store a wake up signal in the semaphore and someone will try to use the wake up signal at the same time, and the same inconsistency problem will happen because of the race conditions, just like I have shown you in the first example in the video of need for synchronization. When two processes are trying to access the same variable like count, the value of count is getting inconsistent, right? I have shown you with an example. So similarly, if I use this semaphore at the user mode, then again the same problem arises. See, this concept is simple. Okay, let me not use my hands, I'll just write it down and I'll explain you. See, now the concept is, let's go to the producer consumer problem. Or if there is a producer and if there is a consumer, if producer is directly giving a wake up signal to consumer and if consumer is not sleeping, then this wake up signal is going to be lost. So semaphore solution helps us in such a way that you need not directly give a signal to that. You please store the signal in a variable, right? And later, and this variable is going to be there forever, right? And later, whenever consumer wants to sleep, it will just check that variable and see if already producer has given a wake up call, so that it need not go to sleep. That is how this variable is going to be useful as semaphore. But now the problem is, since this semaphore is a shared resource, isn't it? It is a shared resource, and the code which accesses the semaphore will now become the critical section, right? And then what happens if two processes are trying to add a value to this and remove a value to this? See, one process will try to add it, which means he is trying to wake up, right? Another process is going to remove it, which means he is trying to use it up so that he need not sleep, right? And now when two processes are trying to access the same variable, again the same problems will arise. What is that? Inconsistency, right? Therefore, implementing semaphores at the user level is dangerous and it will be inefficient. So most of the operating systems will provide some of the primitives, which means the function calls, which will be which are used to access the semaphores atomically, which means whenever anyone is reading it, all the others will be stopped from using it. So read, modify and update, which means read the value, change it and then update the value. All these are going to be taking place atomically, right? So that is called as atomicity, right? So atomically, when we implement all these operations, right, on a shared variable, then that is how this can be used in order to store the wake up calls and then consume it later. So it is a solution which requires help from the operating system. It cannot be implemented at the user mode. So at user mode we will use it, but then not implement it. It is actually implemented at the kernel mode, right? Anything by operating system is called kernel mode. Now let's see what are the various things on this. First one is variables on which read, modify and wake up happens atomically in the kernel mode. So it is going to happen in the kernel mode. Next thing is, there are two types of semaphores. One is called counting semaphore and other is called binary semaphore. So counting semaphore means, okay, I'll tell you about these two by taking examples, or you can, if you can understand it, okay, I'll take examples and tell you what is counting semaphore and what is binary semaphore. So for now, understand that there are two types of semaphores. One is called counting and other is called binary semaphores. So why these two are required is, sometimes there will be some resources which have to be used in a mutually exclusive manner, which means while you are using it, no one should use it. And sometimes there will be some resources which can be used parallelly by many processes. For example, assume that we have a variable and that variable can be used at any time by only one process, then in that case we use this binary semaphore. Binary semaphore supports mutual exclusion, which means if you use a binary semaphore at the entry section, only one process can enter the critical section. And other one is counting semaphore. Counting semaphore advantage is if you use counting semaphore at the critical section, it will allow more than one process to enter the critical section, and all of them can exist inside the critical section parallelly. In case if your critical section supports more than one process operation at the same time, then go for this counting semaphore. Okay, I'll take examples and explain you what is counting semaphore and what is binary semaphore and what are the operations on it. We shall see the code, everything. Okay.